The next example of a harmonic oscillator is going to be given by this potential here. Now you could argue, and you'd be right, that this is not a harmonic potential. Harmonic potentials are proportional to the square of the displacement. This contains both 1 over the square of the displacement and 1 over the displacement. Definitely not a harmonic oscillator. This is what the potential looks like. So because this potential now is anharmonic, if we look at the oscillations in this potential, we will find that the frequency will depend on amplitude, first of all, which is not the case for a harmonic oscillator. In fact, harmonic oscillators are very special in that the frequency is a constant and doesn't depend on amplitude. Wouldn't be true here. The other problem is that if you were to try to actually solve this, try to find the actual motion in this potential, you wouldn't be successful. There's no closed form solution for that. But if you remember, in the very first video in the oscillator series, here in the oscillator module, we said that if we look at motion very close to the equilibrium, then the motion is approximately that of a harmonic oscillator. So we're going to look here at the or near the equilibrium point. In order to find that, we're first going to calculate what the force is on whatever particle it is that undergoes motion in this potential. So the force of R is minus the u dx, or the u dr actually in this case. So u prime of R so that's what we have. Now at the equilibrium are characterized by the fact that the force is 0. Right? The slope of the potential here is 0, means the force is 0. So F of R0 equals 0. So that means, of course, then that minus A over R0 squared plus T to B over R0 cubed is also 0. And we can simplify things a little bit. And we will then obtain there. Okay, so that's the position of the equilibrium. Okay. Now, next step is to expand the potential around this point. To do that, I'm going to make a change of variable to make things a little bit less cumbersome algebraically, so that the equilibrium point is actually at the origin. So we're going to say that R equals R naught plus some delta. And that gives us then that u of R is the same as u of R naught plus delta because of this change of variable. And that is equal to I can rewrite this and I'm going to change variables one more time. I'm going to introduce the variable x, which is delta over R naught. That is kind of a unitless displacement from the equilibrium, but irrespective of its physical interpretation, it just makes things simpler. So we have then the following. That's what we get when we substitute x in here. Okay. Now remember Taylor expansions. In particular, you should remember this one. Well, you don't have to remember it. It's easy enough to find, but if you have 1 plus x to the pth power, it's equal to the following. So using this, we get if you haven't seen this, there's been a term on the order of, in the size, on the order of x cubed. So all I've done here is I apply this Taylor expansion first for p equals -1 here, and for p equals -2 over there. Then the other thing we should realize is we can actually plug in the value for r0 here, and we will find r0 squared. I forgot to put the squares here. They're important. So serendipitously, or actually not serendipitously, but we get these two to be proportional to one another. So we will get then so here I multiplied everything inside here by 2 because I have the 4 down there, just to put it on the same form as this here for the second term. Now we're just going to rewrite this on this form here using the deltas. Right there, and that is u of r naught plus delta. So it consists of a constant, which is not important, as we know. It has no linear term in delta, as it shouldn't, because we are at the equilibrium, and then we have this term in delta. We know that this is going to be on the form of some constant plus 1/2 k delta squared. We can just look here, and we can then identify k in this case is 8 to the 4th over 8ab cubed. We can once again use this expression here to see that we can take b cubed in terms of the a's, since we know that r naught is 2b over a, therefore a cubed over 2b cubed is going to be 1 over r naught cubed, right? And we can get this out of here. So this just becomes a over r naught cubed. So that's our k. And from there, we know that this harmonic oscillator, if the motion is small enough, we have an omega which is the square root of k over m. Therefore, square root of 8 to the 4 over 8 b cubed m, or slightly more simple, a over m r naught cubed. Okay, so that was a fair bit of algebra, but just let's review what we did again here. We found the equilibrium point by setting the force equal to 0, which amounts to also setting the first derivative of the potential to 0. And then we looked at that point, we did a Taylor expansion, and we kept only the constant and the second order term in the displacement away from equilibrium, and from there we were able to identify this k constant, which we found to be a over r naught cubed, and therefore we can say that for small oscillations away from the equilibrium, this is the frequency of oscillation. Okay. Now, this is a useful exercise to do at least once. In reality, though, you don't have to be nearly as complicated. Remember that the Taylor expansion has the following form. Which we then can rewrite because r minus r naught is delta. And we don't care about this term or anything higher than that because that's small. This is going to be 0. This is unimportant. So this is just essentially equal to some constant plus 1/2 k delta square. And by just looking here, we find immediately that k equals u double prime at r0. So that suggests a model for solving this type of problems. And this is really what you should be doing when you encounter this problem in an exam or on a homework. So we have this potential, which is minus a over r plus b over r squared. So to find omega for small oscillations, we do the following. So set the potential to 0, or set the first derivative of the potential to 0, which amounts to setting the force to 0. And then part 2 is k is just equal to u double prime at r0. If k ends up being less than 0, well, then you have an unstable equilibrium. So there's no oscillation in this case. But if k is greater than 0, then omega is the square root of k over m. So that's what you should be doing. The other stuff was really just for illustrative purposes. So let's see if we can make that work in this case. We already know, because we already found it, we already did step 1 above, that r naught is 2b over a. So now we just have to find the second derivative. We'll do the first one first. We already did it above. It hasn't changed, except but now we don't have to worry about the minus sign. And from there we calculate the second derivative. K should be equal to u double prime of r0. Again, using that R naught is 2b over a. And that is the same result that we got up here. They don't fit on the screen at the same time. Well, they barely do. But that's just as it should be. We get the result that gives us that omega is square root of a over m r naught cubed. And this is, of course, much simpler.